Welcome back to ECE 501B. I'm surprised that hasn't happened more frequently this semester. 501B is this lecture that we're talking about. Homework number 7 is due on Wednesday. If you have questions, send me an email and we can see if we can get it resolved that way, or maybe we can set up a meeting. But I won't be able to be in two places at once, so I can't be in office hours, the normal scheduled office hours on this Wednesday. Homework number 8 is due the next Wednesday on the last day of class, as are the 2 deliverables for your project. Deliverable 2 is the main report write-up. Deliverable 3 is really a reflective paragraph of what you learned or what you liked, what you didn't like about the project. That's deliverable 3, and that can actually be appended as the back page on your project 2 or deliverable number 2 report if you would like. But the majority of your effort needs to be focused on deliverable number 2. The final exam is on a Wednesday, and that's 2 weeks from tomorrow. It's been a long holiday break. The final exam is on a Tuesday. Thank you. 2 weeks from tomorrow, and it's from 6 p.m. to 8 p.m. So it will be 2 hours later start time versus the normal class, and it's on a day that we don't normally meet. It's on a Tuesday. So make sure your working arrangements are such that you have the ability to get here on Tuesday, the 11th of December. As I said before we started, we're finishing the Linear Algebra Done Right book this week. Chapters 8 and 9 will be the material for today, but we will really just talk about Chapter 8. That's dealing with the complex situation. Chapter 9 is the complementary real vector space section or material that parallels that in Chapter 8. Chapter 10, we will finally get to determinants. And the trace of a matrix. That is how you do linear algebra done right. But today what we will be doing is talking about generalized eigenvectors for these operators, T. And really it's how do we make a matrix look nice when we don't have a full complement of eigenvectors. We have to build new vectors that allow us to form a basis for our vector space, and those vectors are the generalized eigenvectors. Question? I'm sorry, using strange words. The question was what was full complement. I'm just meaning a full set. I shouldn't have said complement. A full set, a full list of eigenvectors that may not exist to be a basis. Or we have a list, it may not be a basis. That list may not be long enough to reach the dimension of our vector space. So if we do not have n, let's say, linearly independent eigenvectors, then we have to produce new vectors that are linearly independent, and those fall into this category of generalized eigenvectors. And actually the way that we will introduce them today is all eigenvectors will be called generalized eigenvectors. It's just when we find the first one, that is actually an ordinary eigenvector, but it will also be considered a generalized eigenvector. Hopefully that will be clear as we go, but the reason we might need generalized eigenvectors is because these operators that we're playing with may not always be normal. They may not always be self-adjoint in the respective complex or real situation. We may not always have T equaling T dagger in the real case, and we may not have T and T dagger commuting when we're dealing with complex fields. if that's the case, then we can't be assured of diagonalizing these operators. So we'll try to get as close as we can, and that's when we obtain actually the Jordan form, which are ones sometimes sprinkled along the upper diagonal, not on the diagonal. The eigenvalues are always on the diagonal, but we won't have all zeros in our linear operators or in our matrix representation of those linear operators. We'll talk today about the characteristic polynomial and the Cayley-Hamilton theorem, and next time we will, that's my expectation, get into chapter 10, the last chapter of the book, and talk about the trace of a matrix and the determinant of a matrix. And those actually deal with eigenvalues. The trace of a matrix can be found by just summing the diagonal entries of the matrix representation of that operator, but it's also the sum of the eigenvalues with repeated eigenvalues taken into account. And the determinant of a matrix is the determinant of a matrix, or it's also the product of the eigenvalues. That, although I've already covered it, so maybe we can just move on. Next week we will get into the second book, so we've saved the second half of the class for 1 week. That's kind of freebie in terms of material. You will be held accountable for the first textbook on the final exam. But the second book, which by extension goes into infinite dimensions, hopefully now you have a strong foundation based on linear algebra done right. And you can then teach yourself or read ahead or extend your knowledge into the second book over break or after this class is sort of the idea, but we will talk about it next week. That's the plan. Today, as I said, we're talking about chapters 8 and 9. Chapter 8 dealing with complex vector spaces, chapter 9 dealing with real, and it's this idea of generalized eigenvectors. Here's the basic idea. The spectral theorems, we have the complex and the real, tell us that for self-adjoint operators, that's for the real case, have eigenvectors that form an orthonormal basis. In fact, for complex vector spaces, that's not necessary for the operator to be self-adjoint. In complex spaces, self-adjoint can be replaced or relaxed, since being normal is not quite as tight of a restriction, can be relaxed to be normal operators. What that's really saying then is the following. It's equivalent to saying that our vector space V has a direct sum decomposition in terms of one-dimensional invariant subspaces if indeed we have self-adjoint or normal operators. 1D invariant subspaces, meaning we can decompose this vector space into a U1, direct sum with U2, direct sum with U sub 3, direct sum, let's say, to U sub n, where V now, these subspaces u1 through u sub m are associated with the null space of this operator and its eigenvalue, the null space of t minus lambda 1I, meaning an eigenvector can be found in the null space of t minus lambda 1I. That's the definition of an eigenvector. Likewise for t minus lambda sub 2I, etc. And each of those then has a if they each have a one-dimensional subspace or a one-dimensional non-trivial null space, then each of these lambda sub n's, lambda sub j's, are distinct in our representation. If they're all producing one-dimensional invariant subspaces. Question?
Is it accurate to say, since you assuming the eigenspaces are one-dimensional, that you don't have repeated?
So if we have one-dimensional subspaces associated with eigenvectors, then that's not necessarily saying that our eigenvalues are not repeated. Here I'm just saying if we want the best case scenario where we have a direct sum decomposition of one-dimensional subspaces, we're assuming then that all of these eigenvalues are distinct. So there's different ways of thinking about this idea, but here I'm assuming that little n is the dimension of V, capital V, our vector space. But if you had capital V 10-dimensional, maybe you have only 3 distinct eigenvalues. And if now each of those 3 just has a one-dimensional subspace for these null spaces, then you don't have a full list of eigenvectors. You have 3 ordinary eigenvectors, and now we have to come up with a set that will allow us to extend those 3 to give us a basis for that vector space V. That's what we're wanting to do. Here is just the ideal scenario where we have n distinct eigenvalues for an n-dimensional vector space. Then each of those will be a single dimensional subspace producing the eigenvector. But it's not necessarily always going to hold, and that's the next comment. And that's a but. But what about non-selfadjoint or non-normal operators? You can have a self-adjoint operator that has repeated eigenvalues. So that's not what I'm saying. Here I was just saying let's just think about each of these not being repeated. But you could have a scenario where you do have a self-adjoint operator, the identity, for example. The identity operator would be self-adjoint, and it would have a full complement of eigenvectors. A full list. I don't know where that phrase is coming from, but it's sneaking in a lot. But we have a full list of eigenvectors. So now if we have non-self-adjoint or non-normal operators, we may have an insufficient number of eigenvectors. which means that we won't be able to do this decomposition into one-dimensional subspaces. Can't decompose let's say in a one-dimensional way. And that then means that if we were trying to find a nice matrix representation associated with this operator, it wouldn't exist. A diagonal matrix may not exist. We have a lot of buts today, but we can decompose in the following way. Where V now, our underlying vector space, let's say is the null space of t minus lambda 1 I raised to the nth power, where n is the dimension, the overall dimension of our vector space V. So we take an eigenvalue lambda 1, we subtract it through the identity operator with this linear operator t and find the null space. That now might have a dimension bigger than 1 if the lambda 1 is repeated. That now can be direct decompositioned with the null space of t minus lambda sub 2I to the n, etc., up to the null space of t minus lambda sub m I to the n. And we're making the distinction that m is not the same as n in this decomposition, where little m is less than or equal to n, and n is the dimension of our vector space V. And one more piece of notation is we will say little d sub I is going to be the dimension of this null space associated with each of the lambda sub i's. So the dimension of the null space of t minus lambda sub I to the n. So d sub I equal this dimension is the multiplicity of lambda sub I. So if the d sub I is 1, then that's not a repeated eigenvalue. And the dimension of that null space is 1, and you now just have a one-dimensional eigenvector associated with that non-repeated eigenvalue lambda sub I. So that now, d sub I being something other than 1, gives rise to these generalized eigenvectors. Suppose we're now given this linear operator t on this vector space V, and let's let lambda be an eigenvalue of that linear operator t. Then a vector, let's say little v, belonging to our vector space capital V is a generalized eigenvector of t if t minus lambda I raised to the j, and j here is not the square root of minus 1, j is just an integer, v is equal to 0 for some j greater than 0. So j is really greater than or equal to 1. And what you can see is that if we find that little j is 1, or when little j is equal to 1, that gives us our original eigenvector that we've been playing with all class so far. It's just when that subspace or that null space grows as j for different values of j. Then we have generalized eigenvectors. Let's look at some examples to maybe make this a little bit more concrete. This isn't quite the example in the book, so I'm going to say it's like an example in Chapter 8, example 12 in the textbook, but it's not quite the same. Here, let's say that we are given a linear operator t in 3 space operating on a vector z1, z2, z3, and suppose that it produces now z sub 2, 0, z sub 3. That's the linear operator. We're going from a 3 space to a 3 space. It is an operator and it's linear. What's our eigenvalue eigenvector equation? TV is equal to lambda v, or let me just now say tz is lambda z, since we're using z's. If that's the case, then the left-hand side says that z2, 0, z sub 3 for the 3 coordinates of the output of that map, or the result of t operating on z gives us z2, 0, z3. That's supposed to equal a scalar version of z1, z2, z3, or that's equal to lambda z1, lambda z2, lambda z sub 3. That's our eigenvalue eigenvector relationship for this linear operator. What does that tell us? Well, that now gives us really 3 different equations that have to be true for a given set of lambdas. That says that z2 should be just equating the first coordinates on the left side and the right side. The second coordinate is 0 is equal to lambda z sub 2. And the third coordinate says z sub 3 is equal to lambda z sub 3. Or can we now find the lambdas that satisfy this set of equations? And if we start with this one, if this is going to be true for all values of z sub 2, what does that tell us? Lambda is equal to 0. So this says 0 is equal to lambda z sub 2, and if that's true for all z sub 2, that implies lambda is equal to 0. But now if we plug this relationship or use that together with this, we now see that 0 is equal to lambda z sub 2, but z sub 2 is lambda z sub 1. So now we know that lambda squared times z1 is equal to 0. And when is that going to be true? For all values of z1. Then again, lambda is equal to 0, correct? So this now says again that lambda is equal to 0 if it's true for all z1. And finally, down here in the third coordinate, when is that true? For what value of lambda? We can have lambda equal to 1 and z3 is equal to z3 for all z3. So now we know what our eigenvalues are. 0, 0, and 1. And one of those, the 0, is repeated. What's the matrix representation of that operator, or can we now find eigenvectors? What's the matrix representation of this T? What's the top row of A? That just needs to create z sub 2, so it should be 0, 1, 0. What's the second row of A? Pardon? All zeros. And A is going to be square. And what's the third row of A? 0, 0, 1. It just needs to pick up z sub 3. So now we know the matrix representation of A. And if you have had linear algebra, if you've done it wrong, you know what this is, maybe. This is actually a Jordan form representation of our matrix that contains the two eigenvalues on the diagonal, 0, 0, and the third eigenvalue, lambda. So this is actually what's called a Jordan form. It's upper triangular, but it's even more than upper triangular. It has ones possibly on the upper diagonal. And because it has a 1 in that Jordan block associated with the 0 eigenvalues, that tells us something about the number of original eigenvectors that we have associated with lambda equal to 0. We have unique or linearly independent eigenvectors for the distinct eigenvalues. So we should expect at least 2 eigenvectors, right? We have 2 distinct eigenvalues. But now that 1 sitting there tells us we're not going to find a third original eigenvector or a second for the eigenvalue of 0. We have to go to a generalized eigenvector. If, in fact, this was a 0 sitting here instead of a 1, then we would have a diagonal matrix, and we would have 2 linearly independent eigenvectors for that repeated eigenvalue at 0. But because we have that 1 sitting there, we don't enjoy that result. So let's now see what that's now the matrix representation of A. Let's look at finding the eigenvectors. I've already given you the end of the story, haven't I? I've told you the story, but here let's look at lambda equal to 0. Now we are looking at finding non-zero eigenvectors in the null space of this matrix when lambda is equal to 0. And if that confuses you, just say I'm looking for the null space of A, right? Because lambda is 0. This is now just A, and we're trying to find vectors that will be in the null space. But here let's just write down the matrix associated with A minus lambda I when lambda is 0. A minus 0 I. That's just A, and we just wrote down the A matrix. This is now 0, 1, 0, 0, 0, 0, 0, 0, 1. So now let's find the null space of that matrix. We're now trying to find non-zero vectors that satisfy that equation. So now we can just look at each of the rows, right? The first row tells us it says Z2 is equal to 0, because the first row of that A matrix is just pulling off the second component of the Z vector. The second row, what's that tell us? That really doesn't provide us any information, does it? Nothing. But what about the third row? Z3 is equal to 0. So now, what's that tell us about Z1? What can Z1 be? It can be anything. Z1 is now anything, and typically it's convenient to just make it a value that will produce an orthonormal vector. Have it equal to 1. And so this is now an eigenvector for lambda equal to 0. Did we have two variables that we could adjust? No, we just had one Z1 component that could be anything. So now we're stuck with two eigenvalues at 0 and only one eigenvector, original eigenvector. Well, let's continue. Let's now look at lambda equal to 1. Now we do have something a little bit more interesting. When we replace lambda with 1, what does that matrix look like? Now we have minus 1s on the diagonal, but we had a 1 in A in the 3, 3 entry, so that now becomes a 0. We don't touch any of the off-diagonal entries, and now this is our A minus lambda I matrix for lambda equal 1. And if we look at the null space of this, now we are looking at minus 1, 1, 0, 0, minus 1, 0, and 0, 0, 0, operating on our 3 vector, producing the 0 vector. Now we can see from the top row that we have minus Z1 plus Z sub 2 equaling 0, or Z1 is equal to Z2. The second row says that minus Z sub 2 is equal to 0, which now says Z sub 2 is equal to 0. And since Z1 is equal to Z sub 2, we're now forced to have the first two components of our eigenvector associated with lambda equal to 1 fixed at 0. What can Z sub 3 be and still satisfy this equation? Anything. And you could see that by looking at that, and before you could see it by seeing that, oh, 0 is scaling Z1, so Z1 can be anything, and it's not going to give us a non-zero value. Or now, in this case, Z sub 3 is anything, and our eigenvector now, if we select it nicely, can be chosen to be 0, 0, 1. Do these V's form a basis? No, because we needed a list that was 3 long, and we only have 2 in this list. So what about the other eigenvalue at lambda equal to 0? Now we're having to play with or worry about repeated eigenvalues. What did we find when lambda is equal to 0? How many vectors did we find? Eigenvectors. Just one. So there was only one eigenvector associated with lambda equal to 0. Or the dimension of the null space of, let's say, a minus lambda I to the 1 power with lambda equal to 0 was equal to 1. Meaning there's a need for something more, and that need is going to be fulfilled by a generalized eigenvector. Need a generalized eigenvector to create a basis for V, which was in F3. Let's then try to look at squaring this a minus lambda I when lambda is equal to 0. Or look at higher powers of that matrix and try to examine its null space. So let's now examine the null space of a minus, let me just go ahead and put the lambda in, 0 times I squared. That's just a squared, since lambda is 0, or a was this matrix, and now that operates on itself. And what does that produce? Well, if we now look at what the first matrix is doing to the second, the first matrix says, oh, for the first row, just take the second row of the second matrix. And the second row of the second matrix is 0. The second row of the result of this product says just annihilate everything in all 3 rows, or combine all 3 rows with weights of 0. The second row becomes 0. What's the third row? Says, well, just copy down the third row of the second matrix, and the second matrix has a third row of 0, 0, 1. Now what we're interested in is finding the null space in this matrix. The null space now of 0, 0, 0, 0, 0, 0, 0, 0, 1 consists of what? Now z1 and z2 in our 3 vector can be arbitrary, so we could write that as z1, z2, and 0 as our vector, where the z1 and z2 are in our field of numbers. And this set of vectors produce or span the subspace containing the generalized eigenvectors for that eigenvalue at 0. Or we could even say, well, I could write that as Z1, 0, 0, with Z1 being in the field. And in fact, I could do a direct sum decomposition of that two-dimensional subspace. Since Z1 and Z2 could be anything, they were arbitrary, I could now say, oh, and my second vector, let me parameterize it as just having a non-zero second component. And that's now another way of decomposing this null space of this a minus 0I squared operator or matrix. Now we can keep those and append this vector, and now we do have a basis for V. Therefore, F3, which was V, could be thought of now as Z1, Z2, 0, with Z1 and Z2 living in our field or being arbitrary, direct summed with 0, 0, Z sub 3. This is now the subspace containing the generalized eigenvectors for lambda equal to 0, and this is the subspace containing the generalized eigenvectors for lambda equal to 1. And that particular set of generalized eigenvectors is in fact just the original eigenvector for the lambda equal to 1 case. It wasn't repeated, so what I had alluded to earlier on in our discussion was we will call these generalized eigenvectors, but sitting inside those is in fact our original eigenvector. We'll call all of these generalized eigenvectors, but sitting in this first subspace, this now two-dimensional subspace, is one of our original eigenvectors. It was 1, 0, 0, or span of 1, 0, 0. The second subspace associated with lambda equal to 1 is the span of 0, 0, 1. It's one-dimensional, and lambda equal to 1 was not repeated. Note that if t minus lambda I to the jv is equal to 0, then what else do we know? Well, now we know that if I looked at v being operated on by t minus lambda I to the j plus 1, what's that going to equal? Whoops. What's that going to equal? Hopefully you had your heads down. So now if you just operate on the first equation on the left, both sides with t minus lambda I, you're applying t minus lambda I to the 0 vector on the left and on the right, so this better be 0. Since t minus lambda I to the j plus 1 v is the same as t minus lambda I applied to t minus lambda I to the j v, and we already said that that was equal to 0. And 0, when operated on by any operator, is going to map to the 0 vector. What is that saying? Well, all generalized eigenvectors are solutions of t minus lambda I to the n, v equal to 0, with n equaling the dimension of our vector space V. And you could see that if you went back and looked at what we had before, a minus 0I cubed, you're going to get back the same as you had a minus 0I squared. And the subspace is going to be the same. Remember some of these details, and this you'll need to remember for the final. Remember, we can put any operator, let's say t, in our field of complex numbers into what form? Not quite diagonal, but what do we know? If we're dealing in the complex field and you give me an operator, we can now upper triangular. So now we can make this into an upper triangular form by the appropriate set of basis vectors. If we do that, what appears on the diagonal? The eigenvalues are on the diagonal. Is this upper triangular matrix or form unique? Usually it's not. We could play around with this basis set and generate a lot of upper triangular representations, so usually not a unique upper triangular form, and it's only diagonal if what? Pardon? When is it diagonal? When it's self-adjoint or normal, and that is going to happen if we have enough regular eigenvectors, stating it another way. So only diagonal if we have enough regular eigenvectors, meaning we don't have to resort to creating generalized eigenvectors. And in general, these eigenvalues might be repeated. Each lambda is repeated for a given operator a number of times equal to its multiplicity, which we were calling d sub I, where d sub I is the dimension. Not sure I'm being consistent, but the dimension of the null space of t minus lambda sub I to the n. Let's look at a pretty simple or basic example. Suppose somebody says that the matrix representation of an operator T has the following structure. It's 5, 1, 0, 5. If I gave that to you on the final and I said, what's the linear map, could you produce that? Good. So that's the linear map, and this is now its matrix representation. And we can actually see that the matrix representation of this linear map is, in fact, upper triangular. What are the eigenvalues? If it's upper triangular, now we know where the eigenvalues are. Lambda equal 5, and how many times do we see 5 on the diagonal? Twice. So with multiplicity, of 2. So now let's look at the matrix representation of T, maybe I should have just called it A, minus 5I. What's that look like as a matrix? We're just subtracting 5 from the diagonal. And now what is there a non-zero vector that lives in the null space of that? That matrix, when operated on by 0, 1, 0, 0, will give us the 0 vector. What if we now, and what's the dimension of the null space of the matrix of T minus 5I? How many linearly independent columns do we have? 1. What's our dimension? 2. So we take 1 from 2, we see the null space is 1 dimensional. If we wanted to have regular eigenvectors, then we would have wanted the null space of this matrix to be 2. And the only way that that would have happened is if that 1 in the upper or on the off diagonal was a 0. Then we would have a null space of 2, and we could find 2 linearly independent eigenvectors for this particular matrix. That was saying that this guy would have to be 0, that 1, and it's not. So let's continue. Now we have to do something more than just accept the ordinary eigenvectors for this system. So now let's look at the matrix representation of t minus 5i. Let's look at it raised to the nth power, in this case 2. What happens when we multiply 0, 1, 0, 0 by itself? The first row copies the second row, which is all 0, and the second row copies nothing, so we get 0, 0. Now we can find linearly independent vectors in the null space of this. We could say, oh, let's just make it easy. Let's let E1 be 1, 0 again. And what's E2? Well, it could be a lot of different things, but to make it clean, let's just say E2 is 0, 1. Or now we can see that the dimension of the null space of the matrix representation of t minus 5i squared, or maybe I'll do it in general. Let's say here's lambda, and lambda is equal to 5, is 2. The null space dimension of the null matrix in a 2 by 2 matrix is 2. And it's spanned that null space by E1 and E2, where E1 is a regular or a normal eigenvector, or an ordinary eigenvector. Who knows what I'm going to call it Wednesday. Maybe we'll quit playing with eigenvectors. And E sub 2 is a generalized eigenvector. Another fact is that if we sum up these multiplicities over all the distinct eigenvalues, and we said there were m of those, if we now sum those up, what do you guess that equals? That's now going to equal the dimension of our underlying vector space, where these d sub i's are the multiplicities as we've defined them. Now that we have these multiplicities, we can create some new facts. Now we're going to call or define a polynomial called the characteristic polynomial. And that we will write as Q of z, where Q of z is now z minus lambda 1 raised to the d1. So that's now raised to however what the multiplicity of lambda 1 is equal to. Z minus lambda sub 2 to its multiplicity. Z minus lambda sub m to its multiplicity. That is what we will call the characteristic polynomial associated with this linear operator that has these eigenvalues, lambda 1 through lambda sub m. Those are distinct with the appropriate multiplicities d1 through d sub m. Hopefully it's clear that the roots of Q of z are in fact the eigenvalues. You let z equal to any of those eigenvalues, and that's going to force Q to equal 0. So obviously the roots of Q of z are the eigenvalues. Once we have that, now we can talk about the Cayley-Hamilton theorem. And this says the following. Given a linear vector space V, let's go ahead and assume it's a complex vector space, and a linear operator on that complex vector space. And let's go ahead and say that we've now created or built the characteristic polynomial associated with that linear operator t. So that's made up of the polynomial corresponding to the lambdas and the d's, the appropriate collection of those. The characteristic polynomial of that linear operator t, Cayley-Hamilton theorem says then if we applied that same collection of terms, if we replaced t with the linear if we replaced z with the linear operator t, that will satisfy, that linear operator satisfies this characteristic polynomial. Let's look at some example or an example. Let's not worry about the proof. Let's just look at an example. So here is an example. Suppose now we have t of z1, z2, z3 being equal to z2, 0, and can you guess what the third component's going to be? If you've stayed awake during this entire lecture, this is coming back to haunt us. This is now z sub 3, right? So that now the matrix representation of that linear map or linear operator A is 0, 1, 0, 0, 0, 0, and 0, 0, 1. And we now know the eigenvalues of A. This is upper triangular, boom. We now can immediately write down the eigenvalues if we didn't remember what they were. They are now 0, 0, and 1. Can we now build the characteristic polynomial? Well, the brute force way to do it is you've listed all of the eigenvalues, even those that are repeated. So now let's just get linear factors associated with each of those eigenvalues. We have a z minus 0. There's one factor. We have another one, z minus 0. And we have our third factor, which is z minus 1. Or that's z minus 0 squared, which was its multiplicity, times z minus 1. Well, we can simplify z minus 0 squared to just z squared. So our characteristic polynomial is in fact z squared times z minus 1. And what does Cayley-Hamilton say? Now, if we plugged in this linear operator t everywhere we see a z, we should get that polynomial in t satisfying the characteristic polynomial. Or this is now saying t squared, t minus 1, and how do we write 1? As the identity operator, we're scaled by 1, so there is now I, and that's supposed to equal 0. So if we apply it to this matrix, T of A, we now have A squared, A minus I, equaling 0, where A is the matrix representation of T. And let's just convince ourselves of that. Let's do a check, sanity check. What's A squared? Second row is just, the top row is the second row of the last matrix. The second row is all 0. Third row is just a copy of the third row that we began with. So there is A squared. What is A minus I? Is that A minus I? And we said then that Q of A is supposed to be A squared A minus I, which is now hopefully it's clear that the top two rows are nothing. And the third row just copies down the third row in the second term, or the second matrix, and that's 0 as well. So in fact, Q of A, or A, the matrix representation of this linear map, does indeed satisfy its characteristic polynomial. Let's now actually look at another proposition associated with the null spaces and range spaces of polynomials of maps or operators. This now is concerned with the null space and range of a general polynomial, let's just say P of T, and the label on this proposition is that the null space and range of P of T are invariant under T. Stating that, then, is if T is a linear operator on this vector space V, and P is now just some polynomial over the appropriate field, number field, real or complex, then what this proposition says is that the null space of P of T and the range of P of T are invariant under that linear operator T. Let's see if we can follow that through logically. Let's first pick a vector V in our underlying vector space, and let's say that it belongs to the null space of P of T. What does that really mean? If I now have P of T, and just think of P of T as some polynomial collection of this linear operator T. T cubed minus 4t squared plus 6t plus 7i. And now we want to find vectors V that are in the null space of that collection of terms. So what are we saying then? If we now applied P of T to V, what would we get? if V is in the null space of P of t, this will give us the 0 vector, right? What else do we know? And P of t applied to T of V is equal to T applied to P of t V. And that is equal to 0. What? A lot of P's and T's floating around. What are we saying? This is actually saying what about T and P of t? They commute, don't they? So here's a fact. P of t and T commute. P of t is just some generic polynomial. What do we know this is? That's 0, isn't it? So that's why this result is 0. What we don't know is why that maybe middle equality is true. Or why do P of t and T commute? What do we know about P of t? What did I just say it was as an example? It's polynomial in t's, right? So it's just powers of t's. This is just linear combinations of powers of t. And now you can pre-multiply and post-multiply by those powers of t, and you can factor that t to the left or to the right. That's how it is able to commute. So this hopefully shows that TV is an element of the null space of P of t if, so that's what this is saying, that TV is in the null space, or is in the null space of P of t if V is initially in the null space of P of t. Whoa, better be careful. The range of t piece, I will refer you to the text. But it's similar. So what? Well, that now gives us a nice decomposition. Since T commutes with all of these different null space and range space. Here's our theorem, or theorems. Theorems 821 and 829. For V, a complex vector space, T a linear operator on that vector space, lambda 1, lambda 2, lambda sub m, eigenvalues that are distinct, with capital G1, G2 associated null spaces, the corresponding invariant subspaces which are possibly one-dimensional, or I should say possibly not one-dimensional if generalized eigenvectors have to be produced, where G of lambda t is this null space of t minus lambda I to the dimension of V. Then we have a direct sum decomposition of our vector space V of the form V is equal to G1 plus G2 plus G sub n. And there's two more parts of this. I'll go ahead and stop here, but I'll fill those in after class. B is the G sub j's are invariant under T, because those are null spaces, and there exists a basis that will actually block diagonalize our operator T. Instead of having a pure diagonal, now we have block diagonals, and those blocks will be in Jordan form representation. Chapter 9 is just extending this to the real vector space. We played today with complex vector spaces.